Great. All right. So let me introduce myself. So I'm Eric Freundt. I'm an associate professor here at the University of Tampa. And so my specialty is in viruses. I teach virology, microbiology, and also intro biology. I may have had some of you in class who are on the Zoom today. So I actually did my PhD studying the SARS coronavirus. And so the first part of the talk, what I'm going to do is kind of give you some information on SARS and how it relates to coronaviruses in general, and how some of the features of SARS 1, so the virus that's causing COVID-19, actually is named SARS coronavirus 2. So you'll hear me talk about SARS 1 and SARS 2. SARS 2 is referring to the virus that's causing the current pandemic. But I think comparing those viruses is actually really interesting, thinking about sort of why this virus is causing such severe disease and thinking about it in relationship to some of the common cold viruses that we've all been infected with is also interesting, especially when we think about, where do we go from here? Does this virus become something that, circulates within the human population, et cetera? So, first of all, it's really interesting from my perspective. I know some of you were probably, born just before SARS emerged, but what's really been interesting for me is to see sort of the parallels between the SARS pandemic or epidemic and what we're seeing now with COVID-19. So this is from Time Magazine here, and you can see in 2003, right, there were headlines about why the virus spreads, China's cover-up, which we saw kind of happen again, and then this feature, right? How scared should you be? So there's a lot of fear, there's a lot of misconceptions, and hopefully today on this call will be helpful for you to actually look at some data and think about, what does it mean and how do we approach this? So SARS actually emerged very similar to what we're seeing with COVID-19. It was a pneumonia that had unknown causes, right? And it was recognized in southern China, first of all, in the Guangdong province of southern China in winter of 2002. Now, the SARS virus was characterized by causing a disease that was very flu-like. So fever, malaise, chest pain, shortness of breath, and a non-productive cough. And then you would get, infiltrates in the chest radiography. So basically a viral pneumonia. And that's what we're seeing again with COVID-19. And in some cases with SARS as well as COVID-19, that would then progress to acute respiratory distress syndrome that can require or does require intubation. So where did that virus come from, SARS? We actually know quite a bit about where it came from. We're going to talk about where this virus came from, but with the original SARS coronavirus, we know that the reservoir of that virus is actually bats. And so the virus was circulating within bats and then actually happened to find its way into two intermediate species. These are raccoon dogs and Himalayan palm civets. Now, you may have never heard of these animals before, but they're actually trapped in China and brought live to what we would call wet markets, right? And so this is where wild animals are brought in and then purchased for food consumption. And we believe that this was an intermediate host that then allowed transfer into humans. And we have data that suggests that people who worked in those wet markets were also exposed to this virus pretty early on. So what starts in China doesn't stay in China. So what you're looking at here is just an animation of the daily air traffic that would occur under normal circumstances. And of course, some of this has been curtailed, but not all of it. And so just looking at these little yellow dots here, right? This is how we move around on this planet as a species. You think about each one of those little dots containing, hundreds potentially of people. What starts in China doesn't stay in China. And so SARS then spread globally, and the SARS coronavirus spread to 29 countries. And the virus caused about 8,000 cases with about 800 deaths. And so that's a case fatality ratio of about 10%. That's very high for a respiratory virus. But you can see it went globally to 29 countries, caused about 8,000 cases, compared to what we're seeing right now with COVID-19. That's really nothing, right? And it was in the summer after the outbreak first started, the virus stopped circulating in the human population. It basically went away, right? So how did it go away? Well, it turns out that just using public health measures of contact tracing and quarantine enabled SARS to be eliminated from the human population. We did observe during the SARS outbreak this interesting phenomenon of super shedders. So this was very well characterized, and individuals were able to be studied who spread the virus. And you can see these different super shedders here, like 1, 6, 35, 1, 30, 27, who managed to infect a large number of people. Now, this is something that we don't typically see with other respiratory viruses like influenza, and is, interestingly enough, something that looks to be happening with COVID-19. So let's think a little bit about transmission of the first SARS coronavirus compared to SARS-2. So both of these viruses are transmitted via respiratory secretions, right? But with the SARS coronavirus 1, you could also find that that virus was also in feces, urine, and tears. Now, SARS-2 has been documented in feces as well. And so it's been found to be in pediatric patients up to 27 days after documentation of infection. So that's longer than the sort of, 14 days that people are talking about right now. And so the virus is also stable, SARS-2, on fomites. So those are surfaces, right, that you come in contact with. So the shopping cart or, doorknobs, things like that. What we know from a pretty carefully done laboratory study is that the virus is actually infectious for about 3 days on plastic and stainless, but it goes way down if it's on cardboard, probably because it dries out, and this virus has a membrane around it that it needs to be infectious. That's sensitive to drying, as well as copper is great for killing microbes of all different kinds. And so it's only stable there for a few hours. But it can be stable in aerosols as well. So these are pretty carefully controlled laboratory studies. You may have seen recently reports in the news media about the virus being stable for 17 days on the cruise ship. Did anybody see that? Well, it turns out that that's a misleading headline. So what they found in that study is the viral genetic material. They didn't find that the virus was still there and able to infect people. It's basically like the skeleton of an infectious virus. So it means that the virus was there and its genome is still around, but that doesn't mean it's infectious. So this virus, SARS-2, transmitted by respiratory secretions, and it's not believed to be airborne. And so what that means is that as we're talking, coughing, sneezing, right, there's sort of big droplets that come out that can go about 6 feet. And that's why you hear the public health professionals telling you to keep about 6 feet away from people, right? It's not the kind of virus, we don't think, that can be in those very, very small droplets that can just hang around in the air for many hours or days and spread much further. So coronaviruses are actually part of a family of human viruses. So there's 4 viruses that we know routinely infect humans and cause about 1/3 of common colds. And so these viruses are related to the SARS coronaviruses 1 and 2, right? And as well as MERS, Middle Eastern Respiratory Syndrome virus. So we have these viruses that typically cause common colds, and we get reinfected with them throughout life. And then comes these viruses that are causing really severe infections, potentially fatal infections, right? So when I did my PhD, one of the things I was very interested in is understanding why the SARS coronavirus caused such unusually severe disease. So whenever we think about, what makes something unique, right? Typically the answers are found in the genetics, right? So when we look at the genes of the SARS coronavirus, we see some really interesting things. first of all, it's a very big genome. So it has about 30,000 nucleotides of RNA. It's one of the largest positive stranded RNA viruses around. And the genome's similar to other coronaviruses in that it has this big part of its genome dedicated towards replicating its genome, and those are the replicase proteins in blue. Then you can see in red it has this spike gene. So that's the protein that sticks out of the virus that gives it its name, coronavirus, looking like the sun or a crown. And then it has this region where there are actually 9 proteins. And if we zoom in on that region, you can see they're just named like ORFs, ORF3, ORF4, right? All of these different genes here, what was fascinating about them is that they were completely different from any genes that had ever been sequenced. So there was really nothing in the database related to them. And so for my PhD, what I looked at is how those genes actually enable the virus to overcome the host response and whether or not they give it any ability to cause disease. And so we found out that some of those proteins, those accessory proteins, really do contribute to pathogenesis. Now, this virus, SARS-2, also has these accessory proteins. They are a little bit different from the accessory proteins in SARS-1, and it remains to be determined how they contribute to the pathogenesis of the virus. But what we can see is, SARS-1 spread to 29 countries. If we look at, this is just the Hopkins map from today. Down there in the corner, you can see on the left-hand side, 172 countries or regions, right? This virus is spreading much more efficiently than the SARS coronavirus did, SARS-CoV-1, in terms of the cases as well. So why is that? Well, I think there's a couple reasons. First and foremost, when SARS-1 was infectious, or when you were contagious with SARS, right, you had symptoms that were pretty severe already, right? So you had a fever, right? You had a cough, you felt terrible, right? And people could identify you as a sick person, right? Isolate you and begin using precautions to keep the healthcare workers and family members from being infected. With this coronavirus, it's actually able to be transmitted before symptom onset. And so before you know that you're sick, you could be out there infecting people and spreading the virus, and that makes it very hard to contain through traditional public health measures like contact tracing and quarantine. That doesn't mean it's impossible, because we've actually seen some countries like South Korea employ contact tracing and quarantine very effectively to control this virus. Now, what I want to do for the rest of the time that we have together is go through some of these myths that I've seen kind of floating around, and then talk about what some of the data shows. And so I say facts kind of tongue-in-cheek here, because of course in science, right, what we're looking at is what does the best data show. And this is an evolving situation. In fact, a lot of the studies that are coming out right now have not even been peer-reviewed. They're just fast-tracked, right? And they're getting these results out there. So it's important to keep in mind that this is an evolving situation, but yet we can still turn to science to understand what is most likely to be true. And so first of all, some people might look at what's going on, and in fact, I've heard people say this just in passing, that like, this is just an overreaction, right? Like there's 60,000 cases of this, and this is today, right? And we're on an exponential phase of the growth of this virus in terms of cases. But people will look and say, well, there's just not that many cases. This is a really big country, right? It's not a big deal. And what we think from some of the modeling data that's out there is maybe about 1/7 of the cases that we're seeing in the hospital are actually then going to be diagnosed as SARS-CoV-2. So what that means is that there's a lot of cases that aren't being recognized. So it's equivalent to looking at a little tip of an iceberg and being like, well, there's a little bit of ice ahead if you're the Titanic, right? So its transmission is happening. It's occurring rapidly in the community. And in many places, contact tracing isn't even happening anymore. Now, you all know that testing was slow to be rolled out in this country, and still the testing is inadequate. So the number of people in the community who are being tested, if they're not symptomatic, right, is very, very low, if any at all. Now, here's another myth. This virus is just like the flu. So one of the great things about this virus compared to some of the others is just the number of infographics that are out there created right now. So one of the things we know is that this virus is more severe than the flu, right? So that's in pretty much everything that you look at. So in terms of the number of people that get infected by this virus, or the R0 number, right? For flu, we think it's about 1, 1.3. For this virus, it's 2, 2.5. Other estimates are quite a bit higher than that, although I don't think there's really good evidence for it. So when you get this virus, you're going to spread it to more people, right? Now, in terms of the incubation time, right, it can be around for quite a long time before it shows up. About 14 days is sort of the outer limit there. But that's a long time between when you've seen somebody and when you come down with the virus. You can travel the world in 14 days, right? And so one of the reasons why we've seen so much spread. The hospitalization rate, we're seeing at least initial data shows that, you know, a lot of people are actually having to be hospitalized. We'll talk about those statistics more in detail. And then the case fatality rate. So this is changing. It will change as we test more and more people who are asymptomatic, right? As we do those studies to figure this out. But right now, right, we can say with pretty good certainty, this is a greater case fatality rate than influenza, than seasonal flu, right? And maybe on par with some of the major pandemic flus that we've seen in the past. So again, as I mentioned, we have super shedders that are walking around with this virus. And that's something that's also different from what we typically see with influenza. So this virus is not like the flu, right? It's causing more severe disease. It causes a viral pneumonia. Typically when people die from influenza, they die of a secondary bacterial pneumonia, where the virus kind of inhibits your innate defenses. And then some of the bacteria that are normally resident in your upper respiratory tract can get into your lungs. And that causes the sometimes fatal pneumonia. With this virus, it's the virus itself that is causing your lungs to fill up with fluid and causing acute respiratory distress syndrome. So you may have seen this as well. So now this disease primarily affects the elderly. Maybe some of you have even thought it, right? So what you can see is that the death rate, right, goes way up when you get above age 55, right? And it continues to climb. So the death rate is actually pretty low in the demographic that you guys are, right, that you represent. But what's also important to keep in mind here is that if you look at hospitalizations, right, so this is just looking at patients known to have been hospitalized, what percent of them were which age? Okay, so this is just a snapshot. What you can see is that 20% of the patients who were hospitalized were between the ages of 20 and 44 years. Okay, so think about being hospitalized with a respiratory virus. You're pretty sick for them to actually hospitalize you at that point. So definitely not fun. When you are hospitalized, what happens? You're putting the healthcare workers at risk of infection, right? You're taking up resources at that hospital. And so you're putting strain on the healthcare facility. And that's really an important consideration that I think, you know, even those demographics that aren't at great risk for death should be thinking about in terms of overall society. Now, how about this? I mean, we've definitely heard this said, right? The virus is going to go away when it gets warm. So we just need it to be warm. I've even heard people say, well, you know, we can just go in the sauna and everything will be fine, or take a hair dryer and just blow it up our nose. That'll solve everything. That's not going to work. Sorry. But what we can see here is actually seasonality of the 4 coronaviruses that cause the common cold. And then this big black line that you're seeing spike here, right? What is this? Well, this is flu. So when you look at these viruses, right, the peak is shifted just a little bit, but kind of coincides with flu season, right? So it does actually go down in the summer months. Although, you know, you can see a little bit in sort of September going out to sort of May or June. And so this is the typical seasonality that we see. But this virus has emerged, right? It's spreading globally. A lot of times you don't see these seasonal patterns occur until a virus is established in a population. And if you just look at what's going on globally right now, let's take, for example, the Philippines, right? So this was updated a couple days ago, right? Now they're even above this number. So the virus is circulating, it's spreading in the Philippines. What's their weather like? It is hot. It's about as hot and humid as it's going to get, and the virus is still circulating. Now, let's say that you know, we know that some respiratory viruses don't do very well in high humidity and heat. So let's say that this virus kind of disappears from the northern hemisphere in June or July, where numbers go way down. Well, we'll probably see corresponding increases in cases in the southern hemisphere, and then it would just come back as we move into next fall. And so the weather is really not going to be something that's going to cure this. Now, in Britain, this was actually brought up as a possibility of a way of dealing with this. Now, the idea is that if you let enough people get it, then you're going to stop its spread. And that's called herd immunity, right? So what you can see here at the very top, right? All these blue people are not immunized. They haven't been infected. They're still healthy. And then you have one red one that's sick and contagious. And this is the situation that we find ourselves in right now, right? Where the virus spreads very efficiently. Now, if you start to have people who recover, right, they can act as barriers. Now, if you get to about 70% of the population having been infected and recovered and have antibodies to then provide them with immunity, what you get is something called herd immunity. The virus can't spread from the infected individuals very efficiently. That R0 or R0 number goes to below 1. And then, given enough time, the virus would extinguish itself from the population, right? So that is great. And if we get a vaccine, this is exactly what we'll be going for, right? But if we get there naturally, this is what those numbers would look like. So right now, right, in terms of the case fatality rate in Italy, this is because of their overwhelmed healthcare system. The current case fatality rate in Italy is about 10%. So if we think about 70% of our population being infected, right, 232 million in the United States, that'd be 23 million, right? If the case fatality rate is looking like what they're seeing in Italy with an overwhelmed healthcare system. Now, let's say it's lower. Let's say it's down to 0.5%, which some people think that maybe, you know, with all the asymptomatic infection, this is more likely what we're going to see. We're still talking about 1 million deaths in the United States, and that's to get to this herd immunity number. So is that really the answer here? Is that what we want to go for? So some people feel like this is all an overreaction, like we really shouldn't be doing all of this social distancing. This is actually a modeling study that came out of Imperial College in London. And so what they look at is what happens if we do nothing. And that's the really big black, very steep curve there. Then you can see that it comes down depending on what public health measures we implement, such as case isolation, contact tracing, quarantine, and closing schools and universities. So if you look at this in more detail down in B, what you can see is the surge critical care bed capacity. So this is how many ICUs that we have that we can actually deal with the number of cases coming in with appropriate medical care, respirators, et cetera, for those that come down with ARDS. So if you look at school and university closing and case isolation and general social distancing, this model suggests that you can actually stay if those measures are implemented early enough. you can stay under that surge capacity, right? Now, once you stop doing those things, right, you're going to see the numbers go right back up, and that's what happens when you get out of this little blue section there, right? So you see those big curves come up again. So this has to continue, right? If it stops, you're going to see the virus coming back, and I think we're going to kind of see that experiment taking place possibly in real life in China, as they have had very strict measures that have controlled the virus, and now they're easing up on them. And so as long as they're transparent about what happens there, I think we'll be able to see whether or not the virus does come roaring back. Now, the other thing to think about is this idea that the cure is actually worse than the disease, because we all know that this is dramatically affecting the economy in ways that we've never seen before, right? So, but if you think about it, right, the fatality rates and things that may be possible if we say, you know what, let's just soldier on, we're going to go to work, we're going to go to school, we're going to pretend like none of this is happening, or, we're going to just try to sequester those that have pre-existing conditions or the elderly and keep them protected while we go all about our business. Not sure that's possible. What you can see is that we're talking about multiples of millions of deaths potentially in the United States alone. So how much is a human life worth, right? So estimates right now are that during the pandemic, the GDP will dip to somewhere around 30%, a 30% dip or less. So, how much do we place value on human lives? What is a human life worth, right? There's actually statistics around value of human life for insurance purposes and things like that. I can tell you, right, back of the napkin calculation, that if we're looking at pretty much any of these, right, that is equivalent to an entire year's GDP in the United States. Now, you may have heard that you can be reinfected with this coronavirus. Now, the data on this are really interesting because we can look at MERS, we can look at SARS, and we can look at what's happening with COVID-19. And so what we know is that patients are generating an immune response to this virus causing COVID-19, right? Because otherwise, how would they be getting better, right? They are clearing the virus and they're recovering in a lot of cases, right? The vast majority of cases, you recover. So we know that they're producing antibodies. We know that they're producing T-cell responses against this virus. But how long are they going to stay in your system? So this is a picture of antibodies binding to a virus, right? Coating the virus. The way that we are protected either by a vaccine or getting infected with a virus is that our body makes antibodies, and those are specific to only one virus, right? They bind to the shape of that virus, and they basically clog it up so that it can't get into our cells. So we need those antibodies to stay around. Now, right now, the data are somewhat limited. So a study that used 4 monkeys showed that 2 of the monkeys were not able to be reinfected. And those 2 are the only 2 that they tried, because the other 2 monkeys, they actually sacrificed at different points to look at how well they were infected, et cetera. Now, so what that shows, right, is that at least in these non-human primates, right, you can generate an antibody response and it's going to protect you. Now, the antibodies were quite low, the levels were quite low in those studies, so we don't know how long those antibodies would persist. If we look at MERS, right, as an example, what we saw in that disease is if patients had a mild disease or an asymptomatic infection, they didn't make antibodies that would protect them, right? And for SARS patients, we saw antibodies not last all that long. So for some reason, with these coronaviruses, our body makes antibodies, but they just don't stay around for all that long. And so it's possible that this could continue to infect individuals. 229E, this is one of the common cold viruses. So what we saw in a study here is that antibody levels would decline to about baseline after 1 year. Okay, so that's why these viruses, there's only 4 of them, but you get infected with them and reinfected with them. You get this common cold throughout your life, right? Because your body just doesn't make antibodies that stay around for very long. So we don't know what's going to happen with this virus long term, obviously, but I think it's instructive to look at the other viruses. Now, you may have heard that this virus was man-made. There's actually a study that came out in Nature Medicine just very recently. And what they saw when they looked at the sequence of SARS-2 is that it's very similar to viruses that are found in bats as well as pangolins. Okay, so there's a picture of a pangolin there. So another exotic animal that has these sequences. Now, what's interesting about SARS-2 is that it binds to the cellular receptor better than SARS-1, right? So if you were going to make a virus that you wanted to be like a bioweapon, right? What you would do is you would take SARS-1, right? Because you know that infects humans and it causes about 10% mortality. What would you do with it? Well, then you would see, well, how can I make this even better, right? So you might use computer programs to predict how it would bind to its receptor and get in. Well, it turns out that the computer predictions would say that this virus, SARS-2, shouldn't bind well to its receptor. It actually does a lot better than our computer simulations would predict. And so basically the virus outsmarted what we would do as scientists, right? How did it do that? Through natural selection, right? So random mutations in an animal reservoir being selected for its ability to spread. And so we know that just looking at that, this is a natural process, right? Now, pangolin virus, compared to the virus that's in humans right now, those are different enough so that we don't think that pangolins are actually the animal that transmitted this virus into humans. But interestingly, this virus is now spread globally in humans. And so there are other animals that have a receptor that's pretty similar to ours, right? This ACE2 molecule. So it's possible that this virus could then infect other animals and then over time, right, recombine, evolve, and then possibly pop back up. So, you know, we're not done with coronaviruses once we finish, you know, eradicating this virus from the human population. So you've also heard that, well, we just got to hold on until we get a vaccine and we'll have one soon. And that word soon is something that I take a little bit of issue with because, you know, this is a big family of viruses and we don't have a human coronavirus vaccine. Now with influenza, right, and the 2009 swine flu pandemic, we were able to get a vaccine within a year, right? And a lot of vaccine within a year. Well, we already know how to make a flu shot, right? That technology exists. And so it was it wasn't very easy, but it was more straightforward to get an influenza vaccine against that strain. For SARS-2, we don't know how to produce a coronavirus vaccine that is effective in humans. And we need to make sure that before this vaccine goes to humans, it's safe and it's effective. Because in the past, some vaccines have actually, when someone has been vaccinated and then gets exposed to the virus, they can sometimes have even worse disease because of how it interacts with their immune response. So you don't want to rush this to market, right? That could be a terrible mistake. So if we were to get a vaccine within 18 months, just keep in mind that would be a record, right? In terms of time to creating a brand new vaccine and getting it to market. There are clinical trials that have started already. And so I think that is a record and that's reason for optimism, right? There's a company that's able to change the sequence of their vaccine very quickly and have already started clinical trials. So maybe we will have a record-breaking vaccine, but keep in mind those trials need to be done so that we know that it's safe and effective. Now, masks, are they the answer? Well, they could be very beneficial. You know, the data are a little bit mixed, but how many of you have masks right now, right? There's a shortage of masks, and who needs them? Well, I think by and large, those masks should be given to healthcare workers, right? Imagine the situation where you need to go to the hospital, potentially need intensive care, right? And there's just a shortage of healthcare workers who can actually take care of you, right? So in Lombardy right now, it's estimated that 20% of healthcare workers have contracted COVID-19, right? So because there's a shortage of personal protective equipment for healthcare workers, I think it's important that these masks and personal protective equipment get to that healthcare community. Now, CDC has long recommended against masks for community-associated transmission, including during the flu season, and this was even the recommendation during the 2009 pandemic. They recommended against masks. But there is some data out there that suggests that with SARS, masks were effective. Now, this study, keep in mind, it also had the same reduction in risk as having a pet. So if you had a pet or you wore a mask, you had the same reduction in risk, or if you had recently visited a farmer's market. So we're not quite sure that it was incredibly effective there. It may have been you know, a little bit of noise that was captured. So you know, you can choose to wear a mask if you have it. I would say don't go out there you know, trying to get your hands on masks. So the healthcare workers really need those. Now, the other thing people are worried about is that this virus is mutating rapidly. So we're just probably in the early stages, and maybe this has come from like, you know, kind of like Hollywood movies or something, that the virus is going to, you know, adapt to the point where it mutates and then it becomes airborne, and then, you know, it gives you even worse symptoms and things like that. But what we know to be true is that this virus doesn't actually mutate all that quickly. In fact, it has that really big RNA genome. And so compared to other RNA viruses, it has a slower mutation rate. It's actually pretty good at replicating its RNA without making a bunch of mistakes. Now, there are variants of this virus circulating, right? And what's interesting is that when it makes mistakes, those mutations can actually allow us to track the virus as it moves across the human population. But it's very unlikely. There's not a case that I can think of with another virus entering the human population from animals and then mutating to become even more pathogenic, right? If anything, right, natural selection will favor, you know, spread, which typically is less severe disease, right? So you can walk around and get it to others, right? So, all right, so we're coming to close to the end here. So just a couple other questions that I think, you know, have definitely come up in the press recently. This is that, you know, maybe drugs are the answer. And so I think you've probably heard maybe conflicting sides of this, where some people are saying, you know what, we're going to have great drugs. This is going to just solve everything quickly. And others saying, well, hold on a minute, we just don't know. Okay, and it's too early to say so. So I'm going to show you the data, what this looks like. So what we have are these drugs that are anti-malarial drugs. They're also used for other conditions like lupus, but these drugs can reduce virus infection in cells. So this is a figure from a paper that was published very recently where they're looking at how much this drug, right, either remdesivir or chloroquine, inhibits the virus. So the larger the bar here, looking at the x-axis or y-axis is percent inhibition, the larger the bar, the better it inhibits the virus. So what do you see? Well, first of all, chloroquine, right, at this concentration is inhibiting really well, right? If you give it to the cells during the entire experiment, you really reduce virus replication. If you give it right as the virus is getting in, but then you wash it off, right, it still does really well, and that's not true for remdesivir. And then if you give it after the virus has gotten in, right, it's still effective. Now, remdesivir, you can see that it has to be there during the full replication process, right? So this is interesting, and this is just in cells. So then we have to say, okay, well, that's cool, but how does it work in humans, right? So these are the data that have come out from a trial that was conducted in Marseille, in France. And so this was a non-randomized trial. And what happened in this case is basically we saw a significant reduction in viral load. So this is the amount of virus, right, as a percentage of patients that had PCR positive samples. So their sample size was 20 patients here, and we can see it going down. When this drug, hydroxychloroquine, was combined with azithromycin, the results were even better at days 3 through 6, right? So that's initially quite promising. The amount of virus is going down, or at least patients are clearing it more quickly when they have these drugs aboard. However, how does that relate to the patient outcomes? And so that's something that we don't really know at this point, right? And so I think looking at these data, right, you can be on two different sides, and that's, Tony Fauci, the director of the National Institutes of Allergy and Infectious Disease, who you've probably seen in the media, talking about this drug with a little bit more caution than President Trump has been. And so the limitations of this study are that it's a small sample size, right? There's only 20 in the treatment arm, and it was non-randomized, right? So how did they choose that treatment arm? Were those patients more likely to clear the virus, to recover anyways, right? The way that you know that something works is through a randomized, double-blind, placebo, right, controlled trial. And so that hasn't happened here yet, right? If you look at the clinical outcomes here, some of the patients who had this drug, right, went into the ICU, right, and one died, right? So, it's not certainly a cure-all. We also know that these drugs can cause irregular heartbeat and other side effects, including psychiatric or psychological symptoms. And it's important to keep in mind that a lot of drugs that initially show promise in a non-randomized, non-blinded trial, they don't hold up. And so that's where this caution is coming from. Also, right, there's already been shortages of these drugs as people are rushing to hoard them to get their hands on them. And patients who are using them for other conditions now may be limited in whether or not they can actually be treated with them. And so that's something that we really need to avoid. Now, remdesivir is in 9 clinical trials as of yesterday. I looked at clinicaltrials.gov. There's probably more today. But phase 3 results, which is really that sort of last trial, and so we should have good evidence about its efficacy and the side effects, et cetera. That trial was conducted in China, and those results are expected in April. So we should know very soon whether remdesivir, this drug developed by Gilead, is effective as well. So just a couple things before we close. We talked about the responses, and right now what we're seeing in the United States is really a patchwork, right? And so when we looked at the imperial modeling data that showed that if you implement these practices, you can have a great effect. What we don't really know is how they are going to be effective if they're applied unevenly across a population that is mobile, right? So you know that New York is having a shelter-in-place response at this point. Well, a lot of those individuals have come down to Florida, right? And so, as long as we're able to move around, and this is controlled by the states or even municipalities, right? So the city of Tampa may be acting in a way that's different from the county, Hillsborough County. It's really, I think, potentially going to be ineffective at controlling this. Now, this is actually something really interesting that I just wanted to point out to you guys. This is very recent data from a company that makes a smart thermometer. And so basically, you know, you take your temperature and it communicates to an app. And then this company, Kinsa, they can actually see what your temperature is, right? And where you are. And so they've put together this map. It's healthweather.us. You can check this out. And so this is looking at atypical illness. So flu season, right, is upon us. And so we're going to see typical flu-like activity with elevated temperatures. But this is above what we would typically see with flu season, atypical illness, right? And it's moderate to high. So if you look at this map, I think it's pretty sobering that Florida is definitely showing some fever here. And this is recent data, right? That then if we're going to see sort of our healthcare system getting overwhelmed, these people with a fever are going to be starting to go to the hospital, right? Like later this week and next week. And so remains to be seen how this is going to impact ours. Now, I want to just lighten it a little bit here. And you may have seen this, you know, basic idea. Instead of flattening the curve, we're going to catten the curve, right? So what can we do? The things that you're doing right now, right? The things that you're participating in these remote courses, right? And you are fighting this virus, right? So what we can do is we can social distance, we can hand wash, right? We can quarantine and frequently disinfect surfaces. What that's going to allow us to do is reduce transmission of this virus and allow our healthcare system to function in the way that it needs to, so that people who are going in with you know, severe pneumonia can actually be treated, intubated, and then recover, be extubated, and continue on, right? If patients can't, if we don't have enough ventilators to go around, we're going to see those case fatality rates go way up, and that's what we're seeing right now in Italy. So continue with those non-pharmaceutical interventions. They're really kind of the best measures that we have in place right now, and hopefully some of those drug trials will show some great results as well. But at this point, these are the best tools that we have. So with that, I'm going to just look through your questions here. So just give me a second to pull up your questions. And if you have any questions, please go ahead and send them on. So how different genetically is SARS-CoV-2 from SARS-CoV-1? So we can see in terms of the percentages, they're pretty similar. I think I'm hesitant to say the number because I don't want to get it incorrect. We can say that they're very pretty closely related. In terms of some of these accessory proteins, what we can see is that some of them are shortened, right? Some of them are missing. So they've varied those accessory proteins, but in terms of the overall sequence of the virus, they're greater than 70%, but I don't want to put an exact number on that. It's known. I'm just hesitant to give you incorrect information here. So here's a question. When do you think it will be safe to enter back into society? So that's the big question that I think is on everybody's mind, right? So when is it going to be, when are we going to be to a point at which we have, you know, the ability to do this safely? I think if we get drugs that are able to keep people who have, you know, severe disease from really crashing, right? If we're able to reduce that mortality rate and this disease becomes something that's manageable with the drug supply that we have, then I think we probably will move back to sort of normal. Otherwise, what we have to do is wait, right? And continue to social distance to a degree that's going to keep the healthcare system from being overloaded. And so that's going to require longer periods of time until we can get a vaccine and until enough people have this that then we can get to those herd immunity levels. Okay, so questions about why doesn't this virus seem to affect children? So what's really interesting about this is that if you look at what happens with the coronaviruses that infect us, all the time, right? Children, right, generally get sort of a mild disease for this, right? It's possible that when these viruses first emerged into humans, right, they caused severe disease in the elderly who hadn't seen this virus before, right? So we don't know exactly what it is about the immune system of children versus sort of adolescents who are also, very good at mounting an immune response. That's different about those that are elderly and the disease outcomes here, but it's certainly related to their immune status. So here's a question: where do you believe we are in the curve? Well, it's not even about belief. So you guys are all probably very familiar with the Hopkins map at this point, right? And so what you can do is really just look at the map there, click on the United States, and look at our cases. And our case numbers in the past few days have been doing this, right? So we are on the logarithmic side of the curve. And so we're going to see a lot more cases happening. I don't think we're near the top of that curve. I think we're going to see quite a bit more. So related question, like, do you think this virus will last for months? Yeah, I do, because I don't think that, even if we have treatments that are able to mitigate the disease, right, the virus is still going to be circulating. And this virus has shown that it's really good at spreading. And so this is going to continue, right, spreading across the globe. And, we have places in the world where even if we get a good vaccine, there are going to be places in the world that aren't going to have access to it, right? So this virus is going to continue to spread. It may be that this virus becomes something that we see like the other coronaviruses, that it kind of causes a mild illness if you've been infected with it before or been vaccinated, and then it kind of becomes like just one of the common cold viruses. So the question here, is there such a thing as too much disinfecting in this situation? Will this hinder our normal flora? And how might that hurt us more? So that's a really interesting question. We all know that we have more bacterial cells in and on our body, or maybe we don't all know that, but we have more bacterial cells in and on our body than we do human cells. And these bacteria do really important things for us, right? And so I think the question relates to, what happens when we kill all the bacteria and viruses, right? Are we not sort of having the same normal flora? I think it's a very interesting question for a time other than this, right? So in this case, I think the evidence suggests that you're much better off erring on the side of disinfection than not, just given the fact that this virus is something that's circulating widely and causing a pretty high fatality rate for a respiratory virus. So question about how much we should trust China at this point. It's a very good question. I think that they have been reticent to share data in the past. And I think that they have a lot riding politically on the outcome of what happens when they allow people to go back to work, because their economy has taken a huge hit. And so at this point, people need to go back to work. And so, we may not see COVID-19 cases because maybe COVID-19 is not going to be tested for. I don't know. I don't know what's going to happen. I hope that they will continue to be cooperative with the global community. So if I'm living in a house with someone who tested positive for COVID-19, should I assume that I have the virus? Yes, you should make that assumption what we see is that most cases of transmission are people who live together, right, and have close contact. And so, it's very likely that you would have been exposed to the virus. So what I would recommend that you do in this case is assume you have it. You're going to have to be very careful about your own hygiene, right? Make sure that you're frequently washing your hands, you're containing your sneezes and coughs, etc. And you should quarantine for at least 14 days. So a question about, how the economy is going to look after the virus, I really have no idea. We're in uncharted territory here. And, I'm not an economist. I study viral genes and dishes and how they affect cells. So I can't really comment on that. But it is certainly something that's on everyone's minds at this point. If it's possible to have had the virus without knowing you had it, wouldn't all those people contribute to herd immunity? And would it be worth testing for immunity? So yeah, so if you have had the virus and didn't know it, right, then you might be able to be, part of the 70%. But, and this is, just based on the data from other coronaviruses, what we know from MERS is that if you were asymptomatically infected, you didn't know you had the virus, but it was there replicating in your body didn't make very good antibodies to it at all, such that we probably can't even detect those antibodies. So that means that you're probably going to be reinfected. So, it's possible that you wouldn't contribute to herd immunity in that case. Here's a question about that. Can you take antibodies from healed patients and use those for either vaccine research or treatment? So what you can do, right, is if someone recovers, and this was done in Ebola, and it was done with other outbreaks, you can take serum, so the part of the blood that doesn't have the red blood cells, right, and you can passively give that to someone who's infected with the virus. And the antibodies from that one patient can protect the other patient. But there's that caveat, right, that it seems like with MERS, right, you only generate a lot of antibodies if you're really, really sick and then recover. So those cases are going to be fewer and far between than the cases where people are sick, but they recover, but they don't get very sick or are asymptomatic. So, I would say that it's possible, but certainly will be tried, but it might be a limited treatment, just thinking about how much antibody you can actually get from these really sick patients. Okay, so here's a question about peer review of these manuscripts. You mentioned earlier that a lot of novel research about this virus has been fast-tracked without peer revision in order to allow information to be publicized. We've always been told about the importance of peer revision before publication. Do you think the fast-tracking of the data has potentially published invalid information that is added to the hysteria? It's a really interesting point. I think that it's very possible that this is actually happening. Some of the data that's coming out, right, under other circumstances would probably not be seeing the light of day, right? But we're in an unprecedented pandemic situation where we really need access to information quickly. So what you're also seeing as these articles are published is that people are diving in, and the scientific community is basically commenting on these papers, and sort of there's almost like a peer review happening in the public square, right, online. But the flip side of that is the news media is taking really what's published out there first and kind of ignoring the criticisms that are coming out and just running with a sensational headline and trying to sell ads and get you to click on things. So it's important to think about that as well. So let's see, there's a lot of questions coming in here. I'm gonna just take a few of these because I know we're getting up on the hour. But of course, if you're finding this boring, you can always just drop. So maybe I'll just go through them all, right? So wouldn't allowing the virus to infect more people and therefore contribute to the idea of herd immunity be beneficial to the environment in the long run? A dramatic decrease in the human population could help diminish many of the environmental issues present today. So, that is certainly an argument that is absolutely counter to what, public health individuals or professionals are thinking about, right? So, in terms of have humans has the human population gotten too large? I think yeah, it has. Has it gotten large enough that we're really causing a lot of environmental issues? That's true. Are we ready to basically say, okay, virus, run your course, you can have my grandmother or you can have, my spouse? Absolutely not. That's not who we are as human beings. And so I think addressing this with the best tools that we have, and then thinking about those environmental issues, which are also critical. I mean, you think about the way that the global community is kind of coalesced around this. Imagine if we did something similar to climate change and the climate crisis. I think this is creating maybe a good model for us to work off of. In the fall, can we return to classes, on-campus classes? I am optimistic that we will have the possibility of coming back. Now, I think you can look at what I've presented, look at all the data and say, wow, if those drugs don't work, this virus is likely to still be circulating, right? But I think, in terms of a vaccine, we won't be there. But again, SARS was able to be controlled through contact tracing, quarantine, and disappear. Is it possible in this case? It's very unlikely, but maybe we'll be surprised. Do we think that this virus is going to come back like the flu annually? And I think it probably will. I think this is a virus that we're going to see this particular SARS-2 be circulating in the human population continuously, and it will be kind of like a common cold. If we get a great vaccine against it, this may be a problem that goes away. As far as we're concerned, we won't think about it, right? So what protective measures would you recommend when making essential trips out into public spaces? So, again, we talked about masks are something that, really should be restricted to healthcare professionals at this point. What I would recommend is that you are, very conscious about what you touch and washing your hands, right? That 6-foot barrier is also something that I would adhere to, right? So we think that this virus is mostly transmitted through those respiratory secretions, right? And so if you're able to kind of keep away from people as you're out and about, keep your distance, it's likely that those secretions are not going to reach you through the air. And then it's about what you're touching. And so making sure that you're washing your hands frequently, making sure that you're not touching your face and self-inoculating. Okay, so yeah, so someone asking about the mode of action of azithromycin. So what's really interesting about this drug is it's an antibiotic. And you've probably heard before in your life that antibiotics don't do anything against viruses. Well, this is an exception. So there's something about this drug that seems to be effective, particularly in airway cells and in creating an antiviral response. And so the mode of action of it is, I don't think, very well described, but is something that's really interesting, and people are looking at that. Are people who are working at grocery stores and Target and Walmart at high risk? Yeah, they are, because they're coming in contact with a lot of people, right? So I wouldn't say that they're at high risk for severe disease, but they're at high risk for being exposed to this virus, right? So that's something that we all need to consider, right? These people who are providing us, right, with the food that we need, et cetera, they're doing this really essential service. Say thank you next time. Do you think colleges will be again open at the beginning of next semester? How long will we know when it's safe? And so I think what you're going to see is that, you know, we continue to monitor cases as the case levels begin dropping off because of whatever measures we're putting in place, right? When we're not having new cases being described, that's the point at which, especially if it goes on for a couple weeks, right, we're going to say, okay, you know what, let's go back to normal. But that's something that, again, I'm optimistic we're going to get there, but it's something that we're just watching. Why does it seem like every couple years we have a horrible pandemic? So what we have, right, what we know as virologists and public health professionals know this as well. We have viruses that infect every living thing on this planet, right? And many viruses that do that. And they're constantly evolving, and they're under incredible selection pressure to spread effectively. And so, you know, to me, it's almost amazing that we don't have more viruses emerging or spilling over into the human population and spreading this way. I mean, this is very predictable that we would have a virus like SARS to do this, because we know that they can infect humans. We know that they're in an animal reservoir that humans are coming in contact with. So again, the answer to that is, you know, we're just really talking about, you know, the ability of viruses to evolve and then, you know, move into new hosts. And that's something that, you know, we'll continue to see. So it's important that we study these viruses that are not in humans yet, but are in animals and could move into humans. And it's important that we start thinking about, how do we treat those viruses, right? Maybe we can come up with drugs that would treat all coronaviruses, because their replicase proteins are all very similar. So the fact that we don't have a drug that can target coronaviruses is pretty unfortunate. Maybe a failure of sort of our free market economy in terms of drug production. So the elderly with no underlying medical conditions are still more vulnerable to the virus. So yeah, that's true. So we certainly see that a lot of the comorbidities or the healthcare problems that make you more susceptible to severe disease, they're going to correlate with age, right? But we also see individuals who don't have those comorbidities, but have age as a risk factor, who are severely affected by this virus. And so, you know, I think that probably relates to immune status, but is certainly a risk factor there. So the question is about the mode of action for the anti-malarial drugs. So chloroquine. So the way that chloroquine works is it actually is going to inhibit the acidification of endosomes. And so these are basically little vesicles that take in things from the outside, and viruses have to go through those vesicles as well. And so what we know is that by disrupting the pH of those vesicles, there's actually a lot of viruses that need an acidic pH in those vesicles in order to get out and then begin replicating. And so I think we have a pretty good understanding of the mode of action of the anti-malarial drugs. And so I think there's another question there about, you know, hydroxychloroquine can be used as an immunosuppressant, so why does it stop the virus? And again, if the virus is not able to do its initial steps, you know, where it first gets into the cell and then it uncoats and it releases its genome, that can then begin making proteins and replicating its genome. If it's stopped at those early steps, right, that's actually really good. So a question about the population. Would we see less spread in the future of viruses? What I hope is not that we're going to get to some, you know, magic level of the population based on this virus. I mean, I really hope that we don't see a dramatic reduction in population due to this virus. What I do hope is that we learn lessons that we didn't learn as a global community when SARS happened, right? So when I was a PhD student and SARS was circulating, they shut down the animal markets. Those wet markets, they said no more wet markets, right? But then SARS disappeared, and what happened? Well, they went back to having wet markets, right? We know that if you get a bunch of random animals together, right, live animals, literally stacked on top of each other, right, that is basically a generator for novel viruses. When humans are in close proximity, it's going to cause viruses that could jump into humans, right? And so that's something that, you know, really needs to be looked at carefully. You know, I know it's a cultural thing, and I respect that, but you know, what we also know is that's how viruses are able to spread from species to species, and we get these spillover events. So, you know, I hope that's a lesson that we learn. I think looking at these animal reservoirs, coming up with vaccines and drugs that could be useful for future cases is something that we need to actually put government funding behind, right? Because again, if I'm a drug company, I don't want to create a drug for a virus that I don't know is going to ever be a problem. You know, I want to make money on you know, my drugs, and so I think that's a failure of that marketplace. So we need to be able to actually create drugs that are effective, that maybe we don't need to use, right? That'll just kind of sit there. So do we know why our antibodies don't stay around for some viruses? Well, so we don't really know. So this is a problem with immunological memory. So we don't know what it is about these coronaviruses in particular that is causing them to not produce very high levels of antibodies, and for those not to persist, right? We can understand that that'd certainly be advantageous for the virus, and so there's likely to be mechanisms where the virus creates, you know, proteins that are probably interacting with our immune system in order to make that so, but I don't think there's good evidence on why that is yet. So do we know why SARS-CoV-2 doesn't mutate as quickly as other viruses? Yeah, we do actually. So it actually has proofreading capabilities. So a lot of RNA viruses, you know, you can think about almost like autocorrect on your phone. So a lot of RNA viruses, you know, just does that autocorrect really quickly, and it just gives you, you know, garbled words, things that are meaningless, right? So what SARS is able to do is actually use a backspace button, right? So it's able to correct mistakes as it's replicating its RNA. And so those nucleotide excision is actually the process that we're thinking about there, the process where you're actually fixing the mistakes in replicating the genome. So how would having universal healthcare make this situation different? You know, that's an interesting question. Theoretically, you know, we do, I would say that's an interesting research question for someone to dive into, right? Because there's situations right now where we do have countries that have, you know, healthcare for all that are dealing with this virus. And we have countries where that's not the case, right? And so, I mean, those comparisons will be made, but I can't really speak to how that would affect the current outbreak. And then maybe the last question here, what steps do you believe world governments should take to prepare and address another pandemic similar to the one we're experiencing now? Well, so I mentioned that I think, you know, it makes a lot of sense for governments to fund research into the sort of virome of animals that could jump into humans, especially for these ones that we've seen it happen before. Now, in terms of personal protective equipment, the United States has a stockpile of supplies that could be used for a pandemic. Now, the number of masks that they had in that stockpile was, I think, about 1% of the demand. And so the strategic, or the stockpile just wasn't sufficient. right? We need to make sure that we're thinking about our healthcare system as a priority in terms of capacity for manufacturing of a lot of these things. And, you know, I think just given the profit incentives for these companies, we've seen a lot of these things move to places like China, and then be based on current demand. So I think those are a couple ideas, but I'm sure smarter people than me are also thinking about that, and hopefully we'll come up with some good recommendations. Well, thank you guys for being on the call today. I hope that you've enjoyed it and gotten something out of it. My email address is efreuNdt, efreunt@ut.edu. I'd love to you know, chat more with you guys. Maybe we can organize another one of these in the future. But if you have any questions, you'd like to talk more, certainly shoot me an email, and I'll be happy to get back with you. So everyone stay well, continue following those social distancing practices. I know this is crazy, unprecedented times, but this is really the best weapon that we have. And so we want to take us, all of the people on this call, out of the transmission cycle, right? So at least you can do your part keeping yourself out of the transmission cycle. And so be well, and hopefully we'll all be together very soon.